Welcome. In this video, we're going to take a look at what the common ion effect is and how that's going to affect calculations involving chemical equilibria. So first we want to define common ion. So a common ion is when you have two aqueous substances together in a mixture that both contain the same ion. So let's look at some examples. KNO3 and HNO3. When you stick those in water, we know that ionic compounds like KNO3, they're going to dissociate, break apart into ions. And strong acids like HNO3 are also going to break apart into ions. And we do that, we should notice, hey, that these two substances have an ion in common. So they both contain the nitrate ion. In the second example, calcium chloride and calcium sulfate, when they break apart into ions, as they do when they're dissolved in water, we'll notice that both of these substances contain calcium ions. Let's look at one more example, NaHCO3 and Na2CO3. At first glance, they might seem to have something in common because they both have that CO3 there, but actually NaHCO3, this is sodium bicarbonate, so HCO3 is the bicarbonate ion, whereas this one is sodium carbonate. So these two substances do not have any ions in common. So you just want to be careful when you're looking at your chemical formulas. Keep an eye out for these common ions. This will really help you later on as we look at buffers as well. So let's take a look at how common ions affect solubility. So we're going to do a series of calculations that all involve calcium hydroxide. So we're looking at the equilibrium involving solid calcium hydroxide dissolving in water. Here's the Ksp for that dissolving reaction. And first thing we're going to look at is we're going to imagine we stick some calcium hydroxide in pure water. So we set up the ice chart. Since solids are not part of our K expression, actually let's write our K expression up here. We're going to use the same K expression for all these calculations, the same equilibrium system. So we know it's products over reactants, coefficients become exponents, and you leave out solids and liquids. So the reactant is a solid, so it gets left out of the K expression, so we're going to ignore it in our ice chart. And in this scenario, we're taking solid calcium hydroxide and dissolving it in pure water. So initially, the concentration of calcium and hydroxide ions are 0. Some of my calcium hydroxide is going to dissolve, so it's going to create these ions. It's going to create them in a 1:2 ratio. So my ice chart just sets up all the information that I know, and then I'm going to go back to my K expression right here and plug in the values that we know we don't know. So we know what K is. It's 5.5 times 10 to the negative 6. So that's my Ksp, 5.5 times 10 to the negative 6. My calcium concentration, we're using X to represent calcium, and then hydroxide is 2X, and don't forget to square it. Most common mistake is when people forget to square that. And so 2x squared, I got to remember to square the 2 and the x, and then multiply by x again. So that ends up being 4x cubed when I work that all out. And if I'm asked to find the molar solubility, that's essentially the value of x in my ice chart. That's how much of your calcium hydroxide dissolved. And so when I go through and I plug this in my calculator, I should find that x is 0.011 molar. All right, so this, again, is solid calcium hydroxide in pure water, has a molar solubility of 0.011 molar. Now we want to see what would happen if we were to dissolve it in a solution that contains a common ion. So this second scenario, we're imagining solid calcium hydroxide being dissolved in a solution that already contains 0.2 molar sodium hydroxide. So here's where you want to spot that, oh look, these two things have a common ion. And we know that sodium hydroxide, it's an ionic compound, so when you stick it in water, it's going to split apart and make sodium ions and hydroxide ions. So if you have 0.2 moles of sodium hydroxide, it's going to completely split apart, and you'll end up with 0.2 molar sodium ions and 0.2 molar hydroxide ions. The sodium ions don't interfere with our equilibrium at all, so they're just going to be a spectator, so we're going to ignore them. But the hydroxide, we want to recognize, oh, that's a common ion to my calcium hydroxide. So when I set up my ice chart, I'm still going to ignore my reactant because it's pure solid, but when I'm filling out the initial values in my ice chart, instead of them both being 0, like they were in pure water, my calcium ion concentration is still 0, but my hydroxide concentration is 0.2 molar. So when you dissolve something in a solution containing a common ion, what it does is it changes your initial value. So there's going to be some ions already present. So basically we're starting out with some product already there in the solution before this reaction even happens. And then we're still going to generate, some ions in a 1:2 ratio. So my calcium concentration is X. My hydroxide is 0.2 plus 2X. And now I'm going to go back and I'm going to plug it into my K expression. Remember, this is my K expression right here. So my K is 5.5 times 10 to the negative 6. Calcium is X. And then my hydroxide is 0.2 plus 2X squared. This is going to be, kind of complicated math to solve here because we've got this, 2X squared, 0.2, like we're going to do some complicated math. But luckily, remember, notice how our K value is pretty small. And if K is 3 orders of magnitude smaller than the initial concentration right here, and this one is, it's like 5 orders of magnitude smaller than this, okay, then we can make that X is small approximation, which is what we do is we can say, it's great if you even write it out, X is small, so we can acknowledge to whoever's, reading your response that that this is what you're doing. So we're saying that 0.2 plus X is basically just 0.2. So since K is really small, that means X is much, much smaller than this 0.2 number. So I can basically ignore that change. So when I go over here, instead of X times 0.2 plus 2X squared, this 0.2 plus 2X just becomes 0.2. And now this is much easier math to solve because now I got to do is take this number right here and divide it by 0.2 squared, and then I have my answer for X. And when I do that, when I plug that into my calculator, I get that X is 0.00014 molar. Or you could always write this in scientific notation, 1.4 times 10 to the negative 4th molar. So we should notice that the concentration and the molar solubility in a solution containing common ion is much smaller than it is in pure water. So in pure water, when my calcium hydroxide dissolves, its molar solubility is 0.011 molar. But when you dissolve it in a solution that already contains some hydroxide ions, now the molar solubility is only 1.4 times 10 to the negative 4th. So it seems as though the common ion is decreasing the molar solubility, which makes sense because since there are already some ions present in the solution, that means we have to make fewer ions in order to get to equilibrium. So it doesn't need to dissolve as much in order to reach that equilibrium state. So the molar solubility is now going to be smaller, and we'd observe less of my solid dissolving in this scenario. Let's look at one other example here. So we got some solid calcium hydroxide dissolved in a solution with 0.2 molar calcium nitrate. So again, I'm going to ignore my reactant because it's a pure solid. In this case, my calcium ion concentration starts at 0.2 molar. This one starts at 0. It's going to change in a 1:2 ratio. So this one's 0.2 plus X. This one is 2X. That's just a way of organizing my information, what I'm starting with, what my change is. Now I'm going to go back and plug it into my K expression, which is this right here. I know the value of K, it's right there. So I'm going to go plug this in. And I know K is 5.5 times 10 to the negative 6. And calcium is 0.2 plus X. And then my hydroxide is 2X. Don't forget to square it. Remember, my hydroxide gets squared. Boom. All right, so when I do that, and remember X is small, so we can still, K is small, so we can still use this X is small approximation. So I can simplify it and write it like this. 5.5 times 10 to the negative 6 is 0.2 times 4X squared. So now I'm going to rearrange and solve for X. And if you want to see what we're doing here, X would be 5.5. Just if you want to check your algebraic reasoning there. I'm going to divide both sides by 0.2 times 4, and then I'm going to take the square root of this whole thing to solve for X. And then when I plug this in my calculator and solve, I find that X is 0.0026 molar. So I get a different answer than I did in beaker 2, because again, I'm dealing with a different common ion. The calcium versus the hydroxide is going to have different kind of impacts on my math here. But what we should notice they have in common is in both beakers 2 and 3, the molar solubility is less than it was in pure water. So what we're noticing is that common ion decreases the molar solubility, and that's the theme we want to notice from this first part here. Okay, so again, if you are dissolving a substance in pure water, these initial concentrations start at 0. You want to keep an eye out for a common ion. If you're dissolving it in a solution that already contains a common ion, that means your initial concentration for that ion is not 0. So that's what we're noticing here in these ice charts. All right, let me know if you have any questions.